Hello, everyone, and thank you for joining. My name is Moin Ahmadipur, and I'm going to focus on the recent features in the 2025 version of S-Frame Suite. So today I'm joined by two of my colleagues, Siri Sasibat, who is our steel design expert and will be in charge of our steel design solutions today, as well as Chris Brown. He is the senior director in the product management team, and he is in charge of our concrete solutions. He's going to talk about some of our recent concrete features in our concrete design solutions. So for those who are new to the S-Frame suite, I'm going to very briefly introduce the suite to everyone. So at the center of our suite, we have S-Frame analysis, which offers a wide variety of analysis solutions, including linear, nonlinear, seismic, response spectrum analysis, and so on. We have our steel design solutions, S-Steel and S-Path. S-Steel is integrated steel design solution within S-Frame. So as soon as you have your building analyzed within S-Frame, you can directly work on your steel members and go for code check and design of the steel members. And we also offer this functionality in a standalone environment as well, which is S-Path, assuming you have your own analysis results and you want to do your steel design on a member by member basis, you can go ahead and use the S-Path. We have our famous concrete design solutions, starting with S-Concrete and S-Line. So S-Concrete and S-Line are our concrete design solutions for beams, columns, and walls. We also offer foundation design in S-Foundation, and it offers a wide variety of concrete design codes as well. And this is based on a newer platform which offers Python integration as well. We have our timber design solution, which is S-Timber. It is a standalone analysis and design software. And last but not least, we have our powerful section property calculator, which is S-Calc. No matter how complicated your section shape is, you can go ahead and calculate your section properties in a matter of seconds. So today I'm going to focus on S-Frame and S-Timber. Siri will present new features in S-Steel and S-Path. And Chris will take the lead on our concrete design solutions. So starting with S-Frame and S-Timber. So the first feature that I want to present today is automatic generation of wind and seismic loads. So one of the pain points in structural analysis and design is conforming to the building codes and defining the loads based on the site specifications, the building properties, as well as the building code that we are using. So we have now made it possible to automatically generate some of the building code required loads, including wind and seismic loads. So S-Frame looks at the shape of the shape of the building, the plan views, as well as the site specifications and the building code that we're using, generates the wind and seismic loads, and applies them to the right location in the building. I'm using this 10-story building to showcase this feature. And if I turn on my rendering here, I can see that I have concrete columns, I have slabs, I have 2 concrete cores, and some braces in my model. So one of the requirements for the automatic generation of the wind loads is having the floor numbers defined properly. So if I go to my floor plan tool, I can see the floor numbers assigned to each story in my building. So it is important to not have any gaps in the floor numbers. And since this model was created using the multi-story builder in S-Frame, it's automatically taken care of. But of course, if you're doing this manually, you need to be aware that there should be no gaps in the floor numbers. So the other important aspect in this is having rigid diaphragms defined properly in your model. So I can show how rigid diaphragms are modeled here. Each floor has a rigid diaphragm shown in pink, and each rigid diaphragm has a lead node assigned to it at the center of the geometry. So this is important when applying the wind loads in your structure. Now, I need to set the building code that I'm using for this feature, and that can be set in the settings Preferences, and Design Codes tab. We offer a number of different building codes, and today I'm going to use the American building code. For the wind and seismic load generators, we offer the Canadian and the American building codes. I'm going to focus on the American one today. And under that, we have two tabs, one for earthquake loads and the other one for wind loads. So under each tab, we can specify the parameters that are involved in calculation of the loads. I'm going to use the wind loads as an example today. So for example, we have different sections here. We have the wind coefficients, which are related to the building code requirements and the site specifications for the building. We have the eccentricity factors, which are required for creation of the torsional loads in each plan. And we also have the wind pressure coefficients, which can be user specified, or we can let the program determine that depending on the shape of each floor in our structure. Now, I want to go ahead and generate my wind loads. I go to the loads window, and I want to draw your attention to the fact that I don't have any load cases or combinations in my model right now. As I'm generating the wind loads, S-Frame will go ahead and create the required load combinations and cases for me. So to generate those, I go to the edit window, and we have two options for wind loads. One is the open structure wind loads, and the other one is enclosed structure wind loads, which is done according to the building code requirements. So now we have different options. We can go ahead and create our lateral loads only. We can do torsional and lateral loads together, or we can do all load cases at the same time. So I can go ahead and generate my load cases. Before I do that, I can give the new load cases that are going to be created a base name. For example, I'm going to use wind in this case. And S-Frame will let me know that if no rigid diaphragm with lead nodes is found, it's going to go ahead and create nodes in order to apply the generated wind loads. So now my wind loads are generated for me. I can notice that there are 12 load cases generated for me. And I can look at one as an example. I can turn on my joint loads to view those. Let me go to my side view. And I can see that the joint loads are created at each center of rigid diaphragm. And I can go ahead and look at each one independently as well, just to make it more clear. I have loads in the X direction, in the Y direction, as well as torsion in about the Z direction, as I was expecting. So we have this functionality in STimber as well. I'm going to use this model. This model is a little different because it has varying plan view as we go up the height of the structure. So to set the building code, I can do this under the settings and the building code. Let's use the Canadian code this time as an example, and I can see the parameters regarding my wind load generation at the bottom of this dialog. So again, the wind coefficients, the eccentricities, and the wind pressure coefficients, I can set them as required in my project. And I can go ahead and under the define menu, generate enclosed structure wind loads. I'm going to extract all the loads. And I can see that again, 12 load cases were created for me. And I can go ahead and look at my loads as well. Let me increase the size of the loads a little bit so they are more visible in my structure. And I can see that the loads are created at the proper location across each floor. So the next feature that I want to talk about today is mass concrete design for multi-story buildings. We have S-Frame analysis that offers the analysis for our building. We also have S-Concrete, which is a very powerful tool and a very powerful concrete design engine. We have now made it possible to import your structure directly from S-Frame into S-Concrete and do a multi-story design for your concrete elements in your project. So you can do this for concrete beams, concrete columns, as well as concrete walls. And behind the scenes, we are using S-Concrete's powerful concrete design engine model, which is defined in S-Frame. It is a 20-story building. If I want to turn on my rendering for this model, and I can see that majority of my elements here are concrete elements. So at the bottom stories of my building, I have a different concrete grade. And at the top stories, I have a different concrete grade defined. I also have core walls in my structure. I'd like to call them the west core and the east core. And I'm going to run analysis for this entire model so that I have my forces in my members and in my walls that I'm going to use for concrete design. As you can see, there are 6 load cases and 6 load combinations in this model, and the model ran clean. I can go ahead and take a look at some of the results in my structure. So for example, let me take a look at one load combination for this case. The axial forces in my columns, the shear forces in all my members, as well as moment forces in, again, my members. I need to export my model to Access database format so that I can import it into S-Concrete. So under the geometry window, under the file menu, I can go ahead and export to MDB format. So this is a format that S-Concrete will recognize for my concrete design. So I'm going to need some forces. I'm going to use some of my load combinations here, my member forces, wall forces, as well as pier forces. So these are basically the components that I want to export into MDB format, which is a collection of spreadsheets, which I'm going to then import into S-Concrete for mass design of my concrete elements. All right, so I have my MDB file created on the disk now. I'm going to go into S-Concrete, run S-Concrete multi-story designer, which is basically our batch or mass concrete design tool for multi-story buildings. It can currently work with S-Frame and ETABS models. So I need to point to the MDB file that I just created. I can set some filters. For example, I can choose which columns, beams, or braces I'd like to include in my design, which walls or piers I'd like to include, as well as which load cases or combinations. I can also go ahead and look at the management of my walls. So for example, I can, if you noticed in my model, I had 2 cores, and one of them is the west core, the other one is the east core, but they are all comprised of several walls. So what I can do, I can group these walls into more manageable groups. So for example, I'd like to call that west and east cores. And I can choose which piers go into which group. So for example, I'm going to put pier 1 to 22 into the east group, and pier 23 to pier 42 into the west group. I'm going to accept this. And in my next section, I can go ahead and initialize rebars or reinforcements for each set of my elements in the model. So for example, I have the ability to change the design code. I'm going to use the American design code today to be consistent with my bar type. And I can go ahead and define some initial properties for my reinforcement, including the steel properties, the steel ratio, as well as some other properties. So I can do this separately for columns, beams, and walls. And this is only initializing the reinforcements in my sections for me. Now this is done successfully, and instantaneously I can see initial capacity checks for my members. So for example, in the columns tab, I can go ahead and look at all of my sections here. And at the bottom, I can see an instantaneous capacity check for me. If I like to make any changes or do more edits in my design, I can go to the column form. And here I can see all the properties and all the information that are used in my concrete check. If I need, I can update any property here and do instantaneous code check again. And in the next section is where we go ahead and create our S-concrete files that are going to be run behind the scenes. I'm going to ignore any previously created S-concrete files. And I can do this for all my elements in my model, or I can only do this for one set. And I'm going to go ahead and create my S-concrete files here. So it is generated on my other screen here. So I have the S-concrete files generated for all the sections that I studied in my project. And now I can go ahead and run S-concrete batch. So what it does, it basically takes all the S-concrete files that were just created, opens up S-concrete behind the scenes, and runs a complete code check on each and every section in my model. So for example, you can see that for this structure, which was a 20-story structure with probably 100 elements in it, it takes almost half a minute to process everything. So it is pretty fast. It took about 35 seconds to do checks for all my sections. I can go ahead and look at a tabular view of my results for beams, columns, or walls so that I can have an overall information on what's going on in my model. I can go ahead and create different types of reports for my concrete design. I can do PDF report. And this is the PDF report that was created for me. It shows high-level status of each of my sections in my model with nice graphics and everything. I can also do an HTML format as well, which is very helpful when sharing with others. And it gives me a very good overview of what's going on in my model. I can also go ahead and create a full report for each section that's run in my model. And those are created behind the scenes for me, and I can share them with different stakeholders in the project. It opened in the back, so I'm going to create the report now. And now I can see a complete report for each and every section in my model. I can see a high-level status, and there are hyperlinks that I can click on and go to each section, and I can see what's working in my section and what's not. And we have references to everything, every clause reference in the design code as well. So the next feature that I want to focus on today is panel member connections in STimber. So STimber automatically finds the intersections between panels and members and adjacent objects, and it automatically creates the mesh and the connection behind the scenes. But we have now made it possible to give the user the ability to select what type of connectivity they want to have between their panels and the adjacent object. I'm going to use this 3-story building today to showcase this feature. If I look at the finite element behind my panels here, I can see the mesh. And if I focus on these two panels for now, I can see that S-frame has created intersecting joints, and it has created by default a rigid connection between the two. If I look at the results for my panels, I'm going to focus on the same two panels that I just highlighted. I can see that at the intersection of these two, I have a high moment, which is basically a result of the rigid connection between the two panels. So now I'm going to define a pinned connection between the two as an example. So we have introduced this new connection tool, which offers connections between members and panels. I'm going to perform a panel connection today. And we have different connectivity options. Detached, which basically means the two panels have no connection and only have overlapping joints. Or a pinned connection, which will not transfer moments. A rigid body type of connection, which is basically a rigid body across the intersection of the two. And the custom connection, which lets the user define what degrees of freedom they want to be connected or not connected. I'm going to do a pinned connection today, and I'm going to use this as the main panel and connect the other panel, apply the connection. For consistency, I'm going to do it for the other two panels adjacent to this as well. And now I'm going to run my analysis again. It will take a few seconds, but basically STimber has created a connection between the two panels and defined the proper connection type as well. If I look at the finite element model behind the scenes, I can see that the connection line is created at the intersection of the two, and proper constraints are created as well. Now, if I look at my results for the two same panels, I can see that at the intersection, I don't have any moments anymore. And this is a result of the pinned connection. All right, so in the S-frame suite, we constantly try to expand our coverage of our design codes. And in the 2025 version, we will have some new design codes as well, including the steel design codes for the Euro annexes, including German, Spanish, and French annexes. And we are also offering concrete design as per the American GFRP design code guidelines, which Chris and Siri will talk about in the next set of slides. So with that, I'd like to invite Siri to present the new features on STeel and SPAD.
Thank you. And so as Moin mentioned in the upcoming 2025 release of our steel design solutions, STeel and SPAD will allow the engineer to perform the design and code check to a steel structure according to German, Spanish, and French annexes to Euro Code 3 or EC3. And this is in addition to the already supported UK and Singapore annexes. Now I'm in S-frame. This is a simple model of one member made of an I-shaped section representing a column subjected to a combined compression and bending moments about both a major and minor axes. The model has been adopted from example 6.10 in the, as I mentioned, the designer's guide to Euro Code 3. So I'm going to run a linear static analysis and have a quick look at the compression and also bendings for both strong and a weak axis. So to perform a code check, let's launch STeel here. Okay, so we're in STeel. So instead of performing a code check on all selected members in SDO, I'd like to show you an alternative way where the Send to Scratchpad menu, which can be accessed to by right-clicking on the member that we want to perform a code check on. And a brief note on Scratchpads. Scratchpad is a spreadsheet-like utility in SSD, which without the need to revise either S-frame structural model or member design data in SDO. It can be used to interactively with SDO to explore alternative design options of members, and B, overcome some of SDO's limitations in terms of specific design parameters, and C, interrogate SDO code check and all design results. So now let's go to Scratchpad. I just click on. So it's a spreadsheet-like interface is relatively simple to use. Each column relates to an individual design case that is to be checked for the member that I selected. And the top block here of the cell relates to the strength check. And the second block of the cells relates to the buckling checks. And the third block of cells relate to the details that are to be retrieved from SSTU. So for this model, I've already populated the first case beforehand. So, but let me repeat the process. So let first check on the box at the top for case 2, and from the recover detail in the third block of cell, select load case 1, and let's have the strength check at maximum positive strong axis moment, and let's consider the entire length of the member, which is 4.2 meters. Recovered forces. Okay, so now all the data for case 2 has been populated. You may have noticed they are almost identical to those of case 1. The only exception is the KYL. If I look at the descriptive headers, so this is the strong axis effective buckling length. And so if I, from the example 6.10, they were considering the 0.7 factor for the buckling length about the strong axis. So this is, as I mentioned, Scratchpad can be used to explore various design options, and in this case, a provision of a bracing. So we're going to run a code check for both cases. So now let's compare the DCR, the demand capacity ratios for the combined compression and bending for both cases. So for the first case, we can see that we have the DCR of 0.937 for the first case, and for the second case we have 0.941 for the case 2. So we can see that even without the bracing in the strong axis, the member still passes the check, even though with a little bit higher DCR. So now I'm going to go back to Scratchpad and then go back to S steel. So in the previous cases, we were using method 1, and now let's try method 2, which is introduced in this release. So we were running the design code for the German annex, and I'm going to uncheck this option so that we'll be using method 2. Okay, yes. And now I'm going to go back to Scratchpad and rerun my code check. Okay, and now if you remember, for method 1, we have the DCR of 0.937, and for method 2, now we have a DCR of 0.932. So for this simple example, the difference between the two methods appear to be minimal, with method 1 use a little higher DCR than method 2. And before I conclude this session, in addition to the new annexes to Eurocode 3, we have covered today the latest American and South Korean design codes have been added in the recent release of STU and SPAD. So that concludes my session. Thank you. So I'll let Chris continue the presentation. Thank you.
So I'm gonna talk about the concrete products and sort of the updates that we were working on probably in the last couple of years. So this will sum up a little bit of the work. Focus mainly on a new code support for glass fiber reinforced polymer rebar, which is kind of a new trend to fight corrosion in concrete. Just brief release highlights. Support now for the ACI 440 code in S concrete for columns and beams. There were a few other enhancements that we added to it related to other codes, related to shear reinforcement, crack control. There were a few enhancements to multi-story designer that were also part of this release. That's the product that Moeen showed, demoed with the S-frame model. Reminder that it also supports models coming from ETABS, and we've got support now for the latest version of ETABS, version 22. Foundation, a few enhancements to stepped foundations with pads or mats that have steps. And then also support for ETABS version 22 for the import of models to design foundations inside of S Foundation. So focus today primarily on the GFRP. And before that, I want to give a little background on this material and maybe some of the motivations for it. From the design community and such, and as we know that concrete spalls, it deteriorates over time, but one of the primary reasons for that is that the reinforcement is steel, and that steel is subject to rusting and other types of corrosion. So what the GFRP product is trying to do is to reduce or eliminate that reaction with the concrete and the reinforcement. You'll probably see this as you're driving down the road, any infrastructure project. Most common in roads and bridges, not so much in buildings, but exposed concrete buildings could also have issues with this. As well as issues with cracking and those sort of things. And so one solution that is coming out in the industry now is to replace the steel rebar with this glass fiber reinforced polymer bar. And so this has been happening, I would say, over the last maybe 10 years, but in increasing frequency now with new technology to manufacture these products, as well as new codes supporting their design to support engineers with that. And we've been working with a partner in Canada who has plants, a few plants throughout the world, called MST Bar. That kind of produced an idea of being able to incorporate this into the concrete design solutions that we have. Just a bit of background on GFRP as it relates to reinforced concrete. As I mentioned, corrosion is a big deal. So this potentially reduces the corrosion or eliminates it with the inert case of the bars not reacting with the steel, rusting and producing cracking of the steel. The GFRP also doesn't have a problem dealing with salt or chloride, so it's actually good in marine areas near coast with salt water used there as well. It does have a much higher tensile strength than steel, and you can see that from the little curve at the on the top right. You can see the GFRP material, the green line, basically does have a considerable higher stress capability for axial stress compared to steel. But you might also notice that there is no horizontal plateau of this curve, which basically means that it's not really a ductile material, and that will show up in the next slide here. The other thing that's important about it, I think, from a construction standpoint, it weighs, about a quarter of the weight or density of steel, so it's easier to handle, makes it faster to ship and to place, because rebar is basically placed by construction workers on site. But along with the advantages, there are some limitations right now when we compare it to steel. One limitation that is not insignificant in terms of the procurement procedures is that currently you cannot bend this material once it's cured, because it doesn't have is quite brittle. It's glass fiber with the polymer, so it has to be bent in the shop. It has to be bent under controlled conditions and those sort of things. There's also limitations right now to the bend geometry. It's limited to 90 degrees, so that may require some slight changes of the detailing practices for reinforcing elements that have bends to them, like stirrups in beams or ties and columns. Those sort of limitations on couplers right now, because of the material of the coupler and bar terminators still have to be metallic at this point. And one of the research topics that's occurring also here is, because the material is quite brittle, strong but quite brittle, it doesn't really have energy dissipation capabilities like a normal rebar, which can deform. Not really able to be used yet in seismic zones to deal with trying to make the reinforced concrete an energy absorbing component of the model. One of the last ones that I'll talk about here is creep, what's called creep rupture. So this was kind of a new term that we had to deal with when we were looking at the codes with the material. Again, because the material is brittle with a strong tensile capacity, but no yielding. There's the possibility that when the concrete creeps over time, that it could increase the stress in the rebar up to a failure where it could fail in tension. So in order to prevent that from occurring, the stress in the bars is limited under service loads to mitigate from this type of failure. And we see that in the code, how the designs might change And so, the last topic here, this is a new product for the market, relatively, and so users have relied on design software for quite a long time, particularly for concrete. And that's one of the reasons S-Concrete is as popular as it is. So we felt that it was important to introduce the GFRP design into S-Concrete and S-Line and S-Foundation to be able to attract new users who might want to use this material. I'll just talk a little bit about projects. So this is according to MST Bar. There have been a lot of projects throughout the world that have used this, but I would say that if we look closely, that most of them have been on the transportation side or maybe industrial side, and those sort of things, not on the building side at this point, for the various reasons that I was explaining in the previous slides. So, here's a use case in Canada of a wall, an abutment wall for reinforcement, again, which provides durability, being outdoors, and those sort of things, being able to resist the elements without deterioration. The other common use that we're seeing a lot in transportation is the concrete deck to replace the steel rebar with GFRP. So this is sort of in a low risk zone when it comes to the design, being able to use this material to fight durability and corrosion. Same thing with something like a industrial tank storage. Those sort of things. And then there was a big project in Saudi. The Saudis seem to be quite interested in using this material as well, partly because of the polymer needing to be created for the resin as such. So just kind of a summary on the GFRP, say, design part. What has been important is there's been an evolution now of the codes for this product, both on the building side and on the transportation side. On the building side, ACI has been kind of at the forefront, American Concrete Institute, initially providing a guide for use of the GFRP bars, but now, more importantly, codifying it into a building code requirement with mandatory language so that engineers who are using this product can be confident that the code is protecting them from being able to rely on the codes to provide appropriate designs and those sort of things. In transportation, both in Canada and US, with AASHTO, there's been a kind of an evolution of the codes as well, starting back in similar times for the use in transportation, which I think at this point is still considerably larger than what it would be for buildings. Just a little overview of products and kind of the history of where GFRP. So this is sort of a screenshots of one of the products called S-Line, which is a simple and continuous beam design program. We added support for GFRP in S-Line in release 2022.2. So it was the first one, and probably targeting beams, the first product to be able to use. Engineers were able to design by GFRP, as well as other codes, so they could do comparisons if they wanted to do that. As users know, the strength of these products are both the analysis and code check capabilities, but also the reporting capabilities, giving you detailed results for the code check and clauses that aren't being met. If you so you can understand the design a bit. The second product we introduced GFRP to was S-Foundation. So this was just added earlier this year. S Foundation is kind of a new generation product built with the same technology as Timber that allows you to model in 3D and create structural objects, which then have analytical representation, which then are able to be designed. It's got the ability to draw the reinforcement in 3D, so you can visualize reinforcement and those sort of things. And there are uses certainly for foundation elements to be GFRP material. So we're thrilled to be able to introduce that to the community for designing foundation elements, which may be things in the ground with soils that could be detrimental to the concrete as well as in the marine structures. The last product that's designing concrete is S-Concrete section design. So Moeen talked a little bit about S-Concrete when he was showing Multi-Story Designer, which S-Concrete is behind the capabilities of Multi-Story Designer. So we've got now support for ACI 440 or the GFRP in this release of S-Concrete. We have support for columns, which are rectangular, square, and round. And then we have support for beam elements, which are rectangular, T-beam, and L-beam. And that would complete the cycle of GFRP or ACI 440 in S-Concrete. And again, the ability here to both design and document and understand the designs is an important aspect for engineers, particularly for something that's got a new code. What I was showing here is a comparison of ACI 31819, which is the current ACI code for steel reinforced concrete, and ACI 440 to design the same section with GFRP bars. And this is a comparison. It took me a while to get to this point. Basically, if I change any reinforcement or any spacing at this point, I will get a warning. So this is kind of design optimal for the given loads that we have. And what we're seeing is that the top and bottom reinforcement could be the same. The stirrups are slightly different, and that has to do with the reduced strength of the stirrups that are bent. Generally, crack control is more of an issue with GFRP, so it does require more face bars and sometimes closer spaced bars in the tension zone of the section. But when it comes to reinforcing, first of all, we have to qualify because the rebar weighs 490 pounds per cubic foot, where a GFRP bar only weighs 120. So, but if you were carrying this to site or you were shipping it, you would have to ship 52 pounds of rebar per foot versus 17 pounds of GFRP bars per foot. And so I think we're going to see, as the community starts to get more excited about the use of GFRP and the technology to produce it with a similar cost and those sort of things, we have an opportunity now to bring design tools to the concrete community for GFRP. That's all that I have.